Hello everyone, welcome to our channel. This is Dinesh MA, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. In the last session, we understood how BJT can be used as a voltage amplifier and current amplifier. And in this session, we will understand the different configuration in which a BJT can be used and the input and output characteristics of a BJT in different configurations. Let us understand the different configurations in which a BJT can be connected first. Basically, a BJT can be connected in three different ways, and we call these as common base, common emitter and common collector configuration. Let me list out this. Common base configuration, common emitter configuration and common collector configuration. Any BJT circuit considered, there will be two parts in that. One is the input circuit, the other is the output circuit. And when we say common base configuration, this is how a transistor is connected like. I am considering NPN transistor as the example or reference in this case. So this is emitter, this is base and this is collector. So as we can see here, base terminal is common between the input circuit and the output circuit, or in other words, emitter and base terminals will form the input circuit and collector terminal will form the output circuit with respect to base. So this is common base configuration. Now common emitter configuration, here emitter terminal will be in common and circuit looks like this. This is base terminal, this is collector terminal and this is emitter terminal. As we can see here, emitter terminal will be common between input circuit and the output circuit, or base with respect to emitter forms the input circuit and collector terminal with respect to emitter terminal will form the output circuit. Now coming to common collector configuration, here collector terminal will be in common. So common collector looks like this. This is emitter, this is base and this is collector, and here we can see base terminal forms the input circuit with respect to collector and emitter terminal forms the output circuit with respect to collector terminal. So these are the three different configurations what a BJT can be connected in, that is common base configuration, common emitter configuration and common collector configuration. And depending on what is the voltage that has been applied, the input circuit and the output circuit, or the input junction and the output junction will be forward biased or reverse biased. Depending on whether a particular junction is forward biased or reverse biased, we classify the modes of operation of a BJT as cutoff, active and saturation. These are the three modes of operations what we have for any BJT. Now when do we say the junction is in cutoff or the device is in cutoff region? Let us consider the input circuit and the output circuit. So now if I have to say the device is in cutoff condition or the circuit is in cutoff region, then the input circuit should be reverse biased and the output circuit should also be reverse biased. And if I have to say the circuit is working in active region, then the input circuit should be forward biased and the output circuit should be reverse biased. And if the input circuit is forward biased and the output circuit is also forward biased, then we say the device will be working in saturation region. So these are the three different modes of operation, and these are the conditions for the input circuit and the output circuit we have to declare whether the device is in cutoff region or active region or in saturation region. Now let us understand the input and output characteristics of common base configuration. As we just discussed, in common base configuration, base terminal will be in common between the emitter terminal and the collector terminal. And the circuit for understanding the input and output characteristics is shown here. As we can see here, we have the base terminal common between the input circuit and the output circuit. Input circuit has been formed by emitter terminal and the base terminal, and the output circuit has been formed by the collector terminal and the base terminal. And VBE is the voltage between base and emitter terminal. IE is the emitter current that is flowing out of emitter, and VEE is the supply voltage what we are using as at the input end. And VCB is the collector to base voltage between collector and base terminal, and IC is the collector current that is flowing into the collector terminal, and IB is the base current that is flowing into the base terminal, and VCC is the output voltage what we have. Now how do we determine or how do we plot the input characteristics is, first we'll set this VCB at a constant level by varying the supply voltage VCC. Then we'll vary the base to emitter voltage in steps of 0.1 volt by varying the supply voltage VEE, and the corresponding change in the emitter current IE will be noted down. And the variations in IE with respect to VBE for a constant VCB will be plotted, and that will be the input characteristics of the common base configuration. So here the input characteristics is the variations in the input current IE, this will be in milliamperes. So variations in the input current IE for the variations in the input voltage VBE. So VBE will be in volts. So now what we'll do is we'll vary VBE in steps of 0.1, so that what happens here is, because we have used a silicon transistor, this will be off till we supply at least 0.7 volts at the input end. So here, because the input voltage is VBE is 0, the input current IE will also be 0. As we move on towards the positive voltage, there will be a small current flowing, right? And as we cross 0.7 volts, there will be a sudden shoot up in the input current, right? So as we vary the input voltage VBE, the input current IE will also be varied. right? So this is the input characteristics of this circuit for the set value of VCB. Let us say the VCB we can set at different values and check the behavior of the circuit. Okay, so let us say VCB is equal to 10 volts. Now what if I change this VCB? If I decrease the value of the VCB, then the characteristic would be looking something like this. Let us say this is for VCB equals to 6 volts. So there will be reduce in the base current also. So just like that, if I further decrease VCB, let us say this is for VCB equals to 2 volts. So like this, if I decrease VCB, then there will be change in the input current IE. So this is how we plot the input characteristics of common base configuration circuit. Now coming to the output characteristics. So what we do here in the output characteristic is to determine this, we'll set the input current at a constant level and vary the VCB at different steps by varying the supply voltage VCC, and we'll note down the variation, the corresponding variations in the collector current IC, and these will be plotted on x-axis and y-axis. So here on y-axis we'll be having the output current, that is collector current IC, will represent this in milliamperes, and x-axis will be having VCB. This will be in volts, right? So now if VCB is less than 0, then the device will be in, the BJT will be in saturation region. And as we move on towards the positive level of VCB, the device will move into active region and we'll be seeing the changes in the characteristics, right? So now let us plot these curves. So initially here this region will consider where IC is equal to 0. So this will be the condition for IE input current is 0. If in case input current is 0, then there would be no output current, right? In the last sessions we have understood, whenever there is a change on the input current, there will be change on the output current also. So output current is a function of the input current. Now in case if the input current is 0, output current will also be 0, and this region will say the device is working in the cutoff region. So this region will call it as cutoff region. And if there is a change in the input current, if there is a positive input current, then there will be corresponding change in the output current also. So let us say let us consider an input current IE of 2 milliamperes. So for this there will be a 2 milliamperes corresponding output current IC. So these are example data, not the exact data. For analysis we have considered some example data. Now in case if I increase the input current IE further, then the characteristic would look like this. So this is for IE is equal to 4 milliamperes. Further, if I increase current, This will be for 6 milliamperes. Further, this is for IE equals to 8 milliamperes. So now here what we can see is, so while VCB is negative, the device will be in saturation region. So as it reaches at least 0.8 to 1 volts, then the current becomes, the device will be working in active region. So at least till this particular point, this region will consider as saturation region. This is called as saturation region, and beyond this region will call as active region. So this is how we plot the output characteristics of BJT in common base configuration. Now let us understand the input and output characteristics of common emitter configuration of the BJT. The circuit diagram is shown in this diagram. Here what we can see is emitter terminal is common between the input circuit and the output circuit. The input circuit is made up of base emitter junction or base and emitter terminals, and the output circuit is made up of collector emitter junction or collector and emitter terminals. Again here what we have considered is NPN transistor. And the input circuit has been forward biased. So the P-type base is connected to positive terminal of the battery, and the N-type emitter terminal has been connected to negative terminal of the battery, and the voltage between the base and emitter terminal is measured using this voltmeter VBE, and the current that is entering into the base terminal is represented as IB. And the output circuit is made up of the collector and emitter terminal, and the voltage between the collector and emitter terminal is represented as VCE, and the current that is flowing into collector terminal is represented as IC. And VCC is the output voltage what we have, using which we can vary this supply voltage. Now in order to plot the input characteristics, what we'll do is we'll set this VCE at a constant level by varying VCC, and we'll vary the base to emitter voltage VBE by using this supply VBB, and the corresponding changes on this input current IB shall be noted down, and these variations shall be plotted on this as IB versus VBE. So let us call this as IB, which will be in microamperes, and this is the input voltage VBE, which will be measured in volts. So the characteristics, the input characteristics of common emitter looks similar to common base configurations input characteristics. Again here what we'll do is we'll vary the VBE, right, and then the corresponding changes in IB will be noted down. And here as we go on increasing VBE, there will be a small current that flows in the transistor, and as we cross 0.7 volts there will be a sudden shoot up in the input current IB. So let us say like we have set VBE, we have set VBE to 1 volt. Now if I increase the level of VBE, then this is not VBE, this is the output voltage VCE. Now in case if I change the level of VCE, if I increase the VCE, then this will be, let us say, VCE equals to 5 volts. So there will be a reduction in the input current IB. And in case if I further change VCE, then I may have something like this, further reduced IB level. So this is, let us consider for VCE equals to 10 volts. So this is the input characteristics of common emitter configuration. And now coming to the output characteristics. So here what we'll do is we'll set the input current IB at a particular level as constant, and then we vary the supply voltage VCC to make the variations in the collector emitter voltage, and the corresponding changes in the output current IC shall be noted down. So here we have output characteristics is the variation in the output characteristics IC with respect to variation in the output voltage VCE for a constant input current. So here in input current is IB. Now in case if IB is going to be 0, then there will be no output current. So the device is said to be in cutoff region. The device will be in cutoff region. Now in case if I increase the input current IB, then there will be an output current IC flowing like this. Let us say this is for IB is equal to 5 microamperes, right? And further if I increase IB, then again there will be increased output current available. So it looks something like this. Let us say this is for IB equals to 10 microamperes, and further this is for 15 microamperes. This is for 20 microamperes, and further if I increase the IB, this is for 25 microamperes. And here this region, so this is for the voltages lesser than the what is that, saturation level, I mean the VCE sat. So this region will be called as saturation region. And beyond this, this will be called as active region. So this is the output characteristic curve of common emitter configuration. Now let us understand the common collector characteristics of a BJT. Let us get started with the circuit diagram. Let us consider an NPN transistor, and here the collector terminal is going to be common. So this is going to be emitter terminal, and this is base terminal. This is an NPN transistor. Let us connect the voltmeter. So this is going to measure the voltage between the base and collector, and here we'll have one more voltmeter which is going to measure the voltage between emitter and collector terminal. And the input circuit should be forward bias. So this is P type and this is N type. So here we'll have forward bias condition like this. Let us call this as VBB, and this is going to measure this voltage. So let us call this as VBC, and here this should be, the output circuit should be reverse biased. So emitter is N type, collector is also N type. So emitter should be more negative. Emitter should be more positive. So here we'll have battery connected like this, and let us call this as VEE, and this is going to measure the voltage between emitter and collector. So let us call this as VEC. So this is the circuit diagram what we have for determining the common collector characteristics, the input characteristics and the output characteristics. So now what we'll do is, in order to plot the input characteristics, the output voltage VEC will be kept constant at a particular level by adjusting VEE, and will vary VBB to make the changes on VBC, and will note down the corresponding changes on this ammeter. So this is going to give us the base current IB. Likewise, this is going to give us emitter current IE. So now let us draw the input characteristics. So as I just mentioned, the input characteristics is going to be how IB varies with respect to VBC for a given VEC value. So let this be IB in microamperes, and let us have this on scale of 5 microamperes. And x-axis will have VBC, and this is VBC. So now as we go on increasing this VBB, to say the base to collector voltage, the IB is going to be increasing, and the characteristics looks like this. So here the characteristics is different from the other two characteristics, that is common base and common collector characteristics. So here the current levels will be shown like this, and the levels will be depending on the value set for the VEC. So this remains almost constant to the levels of VEC. Sorry, this is VEC2, this is VEC3, this is VEC4, VEC5, VEC6. So this is the input characteristics of common collector configuration. Now coming to common collectors output characteristics, here what we'll do is we'll set the input current at a constant level and vary the VEE, so that we'll have various values of VEC, and the corresponding change in IE will be noted down. So this looks like this. So here we'll have VEC, and on y-axis we'll have IE in milliamperes. This is 0. Let us have the step size as 2. So here as we keep IB equals to 0, so the input current, the input current is 0, there would be no output current. So here we will be having the cutoff region for IB equals to 0. This is cutoff condition, and as we increase the levels of IB, there will be corresponding output current also made available. So let us say like for IB equals to 5 microamperes, so there will be approximately 2 milliamperes of output current on the emitter terminal. So just like that, as we go on increasing IB, there will be increased levels of output current that flows. So here this region will call as saturation region, and this region will call as active region. So this is output characteristics of common collector configuration of BJT. Now let us understand the biasing of BJT. Here we'll know what is DC load line and how to draw the DC load line, and what information does this DC load line conveys. So first thing is DC load line. So DC load line is a straight line drawn across the output characteristics of a BJT that would convey all the possible DC conditions that exist for the circuit for the given resistance values and the supply voltage values. So let us consider a circuit and understand how this DC load line can be drawn. So to understand this, let us consider a circuit which is where a transistor is connected in common emitter configuration. So let us draw this. This is emitter terminal. Let us connect this to ground potential, and this is base, this is collector, and let us connect a supply voltage VCC, and this is the resistance connected to base terminal. Let us call this as RB, and this is the resistance connected to collector terminal. Let us call this as RC, and the current that flows into base, we'll call this as IB. The current that is flowing into the collector, we'll call this as IC, that is the collector current. And the voltage between the collector terminal and the emitter terminal, we'll call this as VCE, and these are the polarities what we have. Now to understand how to draw the DC load line, we need to apply KVL for this path, that is VCC, RC and collector emitter terminal. So if we apply KVL to this path, then that equation will help us to draw the DC load line. Now applying KVL, we can write here, what we can see is across this resistance we have a drop of RC, IC. So now we can write VCC minus RC, IC minus VCE equals to 0. So this is the KVL expression what we have. So RCIC can be written as VCC minus VCE. So this is one important equation what we need. So with this we can write IC is equal to VCC minus VCE over RC. So this is the expression what we have for IC. Now as I said, this DC load line is a straight line drawn across the output characteristics of the circuit. So let us draw the output characteristics. So this output characteristics is IC versus VCE curve. So this is IC versus VCE. Now the DC load line is a straight line drawn across this. So in order to draw this, we need two coordinates, one on IC axis, collector current axis, the other one is on the collector to emitter voltage axis. So how do we get these axes? Is using this equation we can get those axes. Now to get the coordinate on VCE, we can see IC to be considered as 0. In the same way, to get a coordinating point on IC, we should make VCE equals to 0. So let us do that here in this equation. If IC is made 0 here in this equation, then we'll have 0 equals to VCC minus VCE. This conveys that VCE equals to VCC. So let us say this is coordinate A. So on x-axis at VCE equals to VCC, say for example somewhere here where VCE equals to VCC, we'll call this point as A. Okay. In the same way, if I consider VCE equals to 0, then here RC IC is equal to VCC. This says that IC is equal to VCC divided by RC. So this is another coordinate what we have. Let us call this as coordinate B. So IC equals to VCC by RC. Let us say this is IC equals to VCC by RC and call as coordinate B. Now if I join coordinate A and B, I'll get a straight line that conveys all the possible DC condition that could exist for this circuit. So this is how we draw the DC load line. Now what information does this DC load line conveys? Now the output characteristics has got different regions of operations. Let us consider some curves like this. So now we know that this is cutoff region and this is saturation region and this is the active region. This is cutoff and this is saturation region. Now this DC load line says the DC condition that could exist. So this is connected to the operating point related to the BJT. Now for a transistor or a BJT to be employed as an amplifier or a BJT to be used in an amplifier circuit, we should make sure that the operating point is set at mid of the active region. So it should be somewhere here. Should be somewhere here. So if we miss out this, if we fail to set the operating point at the mid of the active region, in other words, if this operating point moves towards this, so say for example here, then the device will be working in cutoff region, so at least a portion of the input signal will be cut off, because the transistor will not be working in the cutoff region, or output current is 0 in the cutoff region. A portion of the input signal will be cut off. So operating point cannot be set here. On the other hand, if I move this operating point towards the saturation region, then a portion of the input signal to be amplified will be having noise. Unwanted hormones will be involved in the signal. So the operating point should not be near to saturation region. So it should be inside the active region, and particularly at the mid of the active region, so that signal will be completely processed. There will be full room for the logic swing of the signal. So the operating point should be set at the mid of the active region. So this is all about the DC load line with respect to BJT. In the next session, we'll understand the concepts of JFETs and MOSFETs. Thank you.